Alright, continuing on with our exponential topic, we're going to move on to growth and decay, which is probably the more of the application style questions that you're going to get on this topic. So one of the most relevant applications to exponential functions is analyzing the exponential growth or exponential decay of a certain quantity, or the increase or decrease over time, okay? Right now, probably what's most relevant is talking about maybe COVID and the amount of COVID cases that are all worldwide or at a certain point. That is really an exponential growth because it started off a little and then got a lot bigger, and a lot bigger, and a lot bigger. And so if you Google like exponential model of COVID cases, if you want more of a real life model to see what we're talking about, that should probably give you something good. So just like with our exponential functions, an exponential growth or decay model, an exponential growth or decay function is given in the form y equals y naught a to the x. Now your y naught, that's your original amount. And then a determines whether it's an exponential growth or an exponential decay. If it's an exponential growth, so if it is exponential growth, a should be greater than 1, all right? Which makes sense because it is repeated multiplication, and if we multiply by 1 over and over, nothing's going to change. But if we multiply by 2, we're going to double and then double and then double and then double, which makes us a lot bigger. For decay, for exponential decay, a has to be between 0 and 1. Because we're going to be multiplying essentially by a fraction, and so getting smaller and smaller and smaller over time. An example of exponential growth would be like bacterias in a culture. I don't know if you've ever done this like experiment in bio or anything, but you get some dirty water from like a lake sample somewhere, put it in a small petri dish, and then see how much bacteria ends up coming out of all of it. Well, that is an exponential relationship, and it can be modeled. It can be modeled by the formula I will write in a bit. Would be bacteria growth in a culture sample so we'll say something like B for bacteria equals 100 times 2 to the x. So 100 would be your original bacteria times by 2 every time. So let's say per hour or per day, whatever time period you're going to measure it off of. An example of exponential growth, of decay, sorry. An example of exponential decay would be, for example, car price, would be the value of a car. The value of a car. So you guys probably would want to know this soon, but when you guys start thinking about buying cars soon, if you buy a brand new car, the second you drive that off the lot, it depreciates a lot in value. So one example that I found, so let's say you go really expensive, you get a $40,000 car, well, there you go. So it's 88% every amount of time period you're measuring that on, whether that be months, whether that be years, I'm not sure, but you will lose a lot of value if you buy a brand new car straight away. Okay, so they are just some models of real-life applications of these questions. Now let's get into what we're going to be asking you to do. So, the population growth, learn to spell, population growth of a country is shown below. So we'll go the year, and then we'll go, just say pop for population, and it's in millions. So we'll have 2010, 11, 12, and 13, and we had 20 million, we had 20.4 million, we had 20.81 million, and 21.22 million. Alright, and that is just our table of values for this. Well, the question may ask you something like, what will the population be in 2030? Alright. Well, essentially, that's asking us, we need to find the relationship. We need to find this y equals y naught a to the x. Now, if I'm going to go back to 2a, just on exponential relationships, we know that for an exponential relationship to occur, okay, that there will be a constant ratio with our exponential functions, okay? We're after the same ratio happening here. So how are we going to find that ratio? Well, we have this 14, then we have 3.5. We get 4 times bigger because I'm dividing the second number by the first number. Well, let's do that a few times here. Sorry, technical difficulties. So, first time, we're going to divide 20.4 by 20, and that's going to give me 1.02. Alright? But what if it's not exponential? Okay? You need to make sure it has a constant ratio. So you should probably do 2 or 3 of these. So then we'll do 20.81 over 20.4. That gives you 1.0201. And then we have 21.22 over 20.81. And that is equal to 1.0197. Now, essentially, let's just take the average of them. So add all 3 of them together, divide them by 3. The average is 1.02. So let's use that 1.02, and that's going to be our A. Okay? So we can model an exponential function as y equals y naught a to the x. Well, we just figured out that a is 1.02. But what is my original amount? Well, it depends on what year you want to start it off with. Because we've been told the 20 million in 2010, I'm going to start there. Okay, so y equals 20 times 1.02 to the power of something. Okay, now we want to know what the population is going to be in the year 2030. Well, how much time has passed from 2010 to 2030? 20 years. I'm going to take the 2 time periods away from each other. Okay, and I'll just show that that's 20. So what we're doing is we're doing 20 times 1.02 to the power of 20. And my final answer is 29.7. Now that doesn't answer the question. The question says, what will the population be in 2030? Well, the population will be 29.7 million. And that is how I finish off that question. Next one, let's do an example of some decay. The population of an endangered species is declining exponentially. So let's say the first one, year. Pop for population. Okay. And we'll go 2000. 2005. 2010. 2013. And then underneath 5760, 4460. So you can see we are going to be getting smaller, and 2960. And then I'll just draw a line. I'll try to draw a line. Let's use a ruler. And just because I can, let's just move that across a little bit. So much better. Okay. Yeah. No. Cool. So for the first part of this question, I want to know what percentage is the population decreasing by? What percentage is it decreasing by? Well, that's kind of the same thing that we had to do before. So here, we were trying to find the ratio for every time. So it's going up essentially by 20%, sorry, by 2% each time. Now we're trying to figure out how much smaller is it going to get. Well, how do we figure that one out? Again, all exponentials can be modeled as y equals y naught a to the x. Well, we've been told the two populations as they've gone down. So let's put them into my equation. Let's start with my original, which is 5760 times a to the x, and that is equal to 4,460. Well, now we know this is 2005. We know this is 2000. We're not going up in years anymore. We're going up in every 5 years for this example. So instead of x, I'm actually going to write 5 because 5 years have occurred. 5 years have passed. Okay? So essentially, what I have to do is rearrange this equation. So we have 4460 over 5760. And I want the fifth root of that, and that is equal to a. And that is equal to 0.95. 5. So that's my first one. Well, I'm going to do another one as well. I'm going to do 2010 and 2005. So just another example. So 3450 equals 4460 times a to the 5. Because again, 5 years have passed. A equals 3450 over 4460 out of 5. And then that is going to be equal to 0.95. So if I'm having 95% of my original every year, what I'm actually doing is I'm decreasing by 5%. Okay, I'm going down 5% every time, because if I have 95% of what I had, if I have 95% of it, I've gone down 5%. So you just need to be careful there that you're not going down 95%, because that would be ridiculously small. We're only going down 5%. So don't confuse those two. Now, the next thing we want to know is by the year 2025. So what will the population be will it be in 2025? Well, we have our model. We know that y equals y naught a to the x. Let's sub in all our values. So we started off with a population of 5,760. And our a is equal to 0.95. So y equals 5,760 times 0.95 to the x. Remember that this population here is for 2,000. So if it's 2,000 and we want 2025, 25 years have passed. So this now turns into 5,760 times 0.95 to the power of 25, which gives me a population of 16,000.
Is it okay if I just like move it
Yeah,
here?
go for it.
All right.